Alright, so I have started the YouTube side and now I'm gonna get to Google Meet. Alright, so Google Meet is working. I'm gonna turn off my video, which is not gonna work anyway, over there, and start presenting. Alright, there we go. So I think that's everything that I need to set up, and then I'll put my focus back on Discord, so this way I can see everything. Oh, thank you, Nathan, for putting in the YouTube channel. Thank you. I'm editing my camera right now. Okay, so I'm not really editing it. I just have not put it back into lock preview mode. Alright. So Marco has a question about the reset of the last D flip-flop that we looked at. Is the reset line supposed to be set to 0 for it to reset? Okay, so that's a good question. Let's go check it out. Alright, so the lecture has officially started, and we want to find out whether a 1 of the reset is going to reset the content of the D flip-flop, or whether a 0 is going to reset the D flip-flop. Alright, so this is something that you can actually figure out, based on what we already understand about logic gates. Alright, so this is the diagram. Okay, this is the D flip-flop that is resettable, because there's a reset or clear. Okay, so we want to be able to know, how to reset the content, which is this particular SR latch, so that it becomes 0 again. Okay, all right. So now what we need to do, so there are two ways to think about this. Okay, one way to think about this is to think about it kind of backwards. So we look at this particular SR latch, and we say we want it to be 0. What does it take, to make it 0? So we need the reset pin to be a 0, so that the SR latch becomes a 0. So this R would become a 0 if the reset line is a 0 for the AND gate. So for the AND gate, if it is a 0, then it will for sure reset. And then for the OR gate over here, when the reset line is a 0, because this little bubble here means it is negated, and this is a regular OR gate, so that guarantees the set pin, or the S pin, is going to be a 1, which then will guarantee that the SR latch is resetting to 0. So the answer is, when the reset pin is a 0, it would reset the content of the SR latch, not when it is a 1. So I might have mistakenly said it is a 1 in the previous lecture. Alright, so the next question is, okay, yeah, sure. Grant, you're welcome. So Alfred has a trivial question of, what happens when there are no students enrolled in the class in a given semester. So it depends on whether it is actually absolutely zero or whether it is just really a low number. So technically speaking, with a regular class, this is not a regular class because we have two labs combined into one single lecture. So for enrollment purposes, there are actually two classes. We just have the same time for the lecture. So for a regular class, if enrollment is less than 22, then it is kind of like questionable. But most deans would probably let it go. Let the class go, even though the enrollment is a little bit less than 22. But at some point, the dean, who kind of is the manager, of a division, can say, this class is low enrolled, and then it can get canceled. So I cannot tell as. Oh, okay. So it depends on which class. For classes that are only offered once a year, okay, those classes, or for classes that are capstone classes, like people need that class to get a degree or certificate, those classes tend to have a higher tolerance, which means even though they are very low enrolled, the dean will still let it go. For classes where there are multiple sections per semester, then it is not going to be as lenient. So for those classes, they can get canceled pretty easily. So it all depends. Okay, so there are a lot of dependency on whether a class is offered often or not. Yep. All right. So last time, when we ended the lecture last Thursday, we were talking about railroad switches, which was basically. Okay, so there's a SSE9194 who wants to join the call. I'm going to let that person in because I can always kick people out later. So I just want to bring up, if you want to join the Google Meet, you probably want to make sure that your name, at least as it appears, on my screen, is your actual name of a student, because otherwise I might. Yeah, right. SSE9194 sounds legit. So you might want to change that so that I can identify you. The best way is really sign into apps.losreals.edu and then use that particular Gmail account to sign into Meet, because in that case I don't need to admit people in. I mean, you can automatically get into the Meet if you are signing in using apps.losreals.edu. All right. So there is that, and I'm checking the text channel. Nothing else. Very good. Exactly. Thank you, Aaron. And I find that mobile devices, you can just add your apps.losreals.edu account on your mobile device, and you can basically have many different Gmail accounts all active at the same time. So when you sign into Meet, you can just choose which account you use to sign into Google Meet on a mobile device. So it works on a laptop computer, it works on a mobile device. It doesn't matter what you're using. So now we are going back to the multiplexer versus a demultiplexer. So the only difference between those two is really just the direction. A demultiplexer has one single input and multiple outputs. That's a demultiplexer. And a multiplexer is like what this diagram has here, which is multiple input and only one single output. And the job of a multiplexer or demultiplexer is really just acting as a switch. Okay, it's just basically saying which end is connected to the single either input or output, which point connects to the single input or output. All right. Cool. It's not exactly an if statement. It's more like it's not a switch statement either. It's kind of like an array indexing kind of thing. This is your index, and you are basically selecting which one of the input points connect to the output point in this case. All right, so letting more people in. Okay, So what we'll do today is we're getting ready for tonight's lab. So tonight we have a new lab, and we're getting back to the old routine of doing the lab right after class. So the lab is due at 9:50 p.m. Yes, I thought about it before I said it. 9:50 p.m. Um, and this one is kind of the first one that you're gonna the first one that relates to programming using TTP, Text Toy Processor. Um, so what we'll do is we'll make sure that we have all the knowledge, in order to do the homework. Yeah, it's not going to be that bad. That's not going to be that bad. So, so what we'll do today is we're going to take a look at some of the components. So switches, we are already pretty much done with those. And the more complex devices that we have not talked about, one is ROM and the other one is RAM. So just like those infomercial, I have already prepared ahead of time. I have already prepared a circuit, so we can start playing with it right away. So we can start with either RAM component or ROM component. I got two subcircuits here. One is test ROM and one is test RAM. Test ROM is the easier one, because read-only memory, that's what ROM stands for, has very few connection points. Okay, so the idea is you have an A port, which stands for address. You have a D port that stands for data, and you have a cell port that stands for select. Okay, so when the cell, so I have I have pins connected to every single one of these ports. So the A port is an input port, which means the A port is allowing something outside of the ROM to select one of the locations in the ROM to be addressed. The cell port is a single bit input port, and its only purpose is really to say, is this particular ROM component selected or not. It is really the same thing as EN, or the enable of a gated D flip-flop. So it really serves the same purpose. Basically, is this device selected? But obviously, a ROM cannot be updated because otherwise it wouldn't be read-only. And then the D port is output only. Basically it is the content at the location that is addressed by the A port. So for the most part, a ROM is kind of more or less like a read-only array if you want to equate it to a C concept, a concept in C programming that you're already familiar with. So if you want to equate a ROM as an array, then whatever you present to the A port would be the integer that you present inside the square bracket, which is the index. And then the D port would correspond to the value of the element in the array that is addressed by the whatever you present on the A port. The select pin, so the question is, why do we need a select pin? Why don't we just make a ROM, always selected? The answer is, in a real computer, a lot of times the ROMs are, they also can be configured in a multi-drop fashion. In other words, we have a whole bunch of ROM connected to the same A port and connected to the same D port. But each one corresponds to a different range of addresses. And then the addresses would then be used to calculate which ROM is going to have the cell or the select port being a 1. And that way we can, because you can't, okay, in the early days, okay, ROMs can only have like 16 kilobytes of data, okay, which is not a whole lot, right? I mean, obviously by today's standard that is like not much. So one single ROM usually cannot supply the content required by a computer. So a computer typically has a whole bunch of ROM chips in order to specify the entire address space where the ROM content is needed. But as a result, you end up with like many of these chips basically connected to the same A port and connected to the same D port. So the only difference is they are all controlled by different selection ports. So the selection ports will basically be decoded based on the higher bits of the address bits that is not actually presented to the address port here. and then the correct ROM of that range of address space will be active in order to retrieve a content. So for the purpose of our discussion here, it's not going to be an issue. Okay, we only have one single ROM in text toy processor, so the select pin is basically always enabled because there's no need to turn it off. All right, so I'm looking at the text channel. Andrew asked, are modern ROM chips still only able to be written once? It depends on the application. So mobile devices, some do not have a what we call an OTP ROM. OTP stands for one-time programmable. So OTP ROM basically once the factory program it, it can no longer be changed. So that gives you the lowest level, the fallback, bootstrap option. If all fails, okay, you can still rely on the OTP ROM because that cannot be changed. So those devices are much more difficult to be bricked, in modern terminology. On the other hand, we do have flash, right? Flash memory, which acts like ROM most of the time, but they're programmable. Okay, so if you reflash a mobile device using the wrong image, you can potentially render the device unusable. In other words, you can end up bricking, BRICKING, bricking your device. It becomes unusable because there's no way to change the content of the ROM unless you desolder the chip and then use an external programmer to reprogram the content of the device. Somebody suggested a Eeprom. Yes, so Eeprom stands for, okay, so since you guys are mentioning this, sometimes I mention this in this class and sometimes I don't, but since you guys are already on this track, I might as well just talk about it. Alright, so here's a new page. So we have the usual ROM, okay, which is read-only access memory. And then we have PROM, which stands for Programmable Read-Only Access Memory. So the only difference between a ROM and a PROM is a PROM is typically programmable possibly one time. So you're basically buying a blank ROM from the factory, and then you have a special device so you can burn in the content of the ROM, at a manufacturing facility, but it cannot be changed after that. So a PROM is basically a ROM, but it's not programmed by the chip manufacturer. It is programmed later on, so that whoever is putting the PROM into its own, their own circuitry, have some control over the content of the ROM. And then comes Eeprom, and the E stands for Erasable. So now we have Erasable Programmable Read-Only Memory. So Eeprom is interesting because it is usually UV erased. So there's a little window on top of the chip, and if you expose the chip to strong UV light for about 15 minutes, then it will lose its content and then it can be programmed again. You can also expose it to the sun, but it will take much longer under the sun in order to erase the content of Eeprom. And then we have EEPROM. EEPROM, it does not stand for it's actually okay. So EEPROM stands for Electrically Erasable Programmable Read-Only Access Memory. So the extra E stands for electrically. So with EEPROM, you don't need a UV source, and instead you use a different voltage applied to a certain pin, for a certain amount of time or a certain pulse pattern or whatever, in order to erase the content of the ROM, and then it becomes programmable again. So EEPROM is electrically erasable and not by UV. And then after that, we have flash memory, which is based on a different technology. I do not truly understand the mechanism of flash memory. But flash memory is interesting where you do not erase the entire device. You erase basically one sector at a time. But it has a limited number. All of these have limited number of cycles. So with Eeprom, um, they can be erased only so many times, and then after that, the device can no longer be programmed. Flash is really the same way, and that's why when you purchase an SSD, one of the things that you might want to look up is basically how many times can a sector be overwritten. So it's a whole lot more complex than that, but there's a certain measurement of how many times you can overwrite the content of the device, and that's one of the things that you might want to look at when you're purchasing an SSD. All right, so I'm trying to catch up with some of the text messages. No, mechanically, I mean not mechanically, but electrically, ROMs and RAMs are entirely different. RAM can change a whole lot faster compared to any flash memory. RAM is changed while it's running. EEPROM is changed by a different device. That is true, and flash is interesting too. When flash memory is being changed, it cannot be used to supply content. So that's kind of like a tricky thing because you cannot run a program from flash memory and update the flash memory at the same time. Not usually, okay, unless the device is designed to do that. Flash memory cannot do that. It depends on at which level. I'm addressing Luke's question. Is Aaron technically correct? So it depends on at which level. At the abstract level, Aaron is correct that flash any type of flash memory is can the content can change. Okay, so at the abstract level, it is true. But at the circuit level and also at the timing level, it is not true because the way we overwrite memory when it comes to RAM is a very simple operation. But when it comes to flash memory, it is actually it's from the programming perspective, it is also entirely different. Okay, so when you look at instructions inside the computer, the instruction to update a location in RAM is super easy. But if you want to change the content of a location in flash memory, you actually have to run a subroutine to do it. It is actually fairly complex. So there you have it. Hard disk drives can simultaneously read and write. They cannot do that because the bus does not let it happen. Okay, because when we are talking about bus, which is PCI Express, or other kinds of bus, basically it's just an interface. It is unidirectional. So you're either updating the device or you're reading from the device. You cannot be reading and updating the device at the same time. They just don't have the provision to do simultaneously bidirectional access to the device. All right. With SSD, maybe, but it still depends on whether the bus let it happen or not. Because a lot of times when you're reading from an SSD or anything that is high speed, you're using DMA, direct memory access, and DMA is a mechanism that is done by what we usually call a chipset, which is not really central to the core of a processor, but is a peripheral device that is very close to the processor. And the DMA controller can be set up to read a block of memory from a certain device, or it can write a block of data to a I/O device, an input/output device. But it cannot read and write at the same time. And once again, it has to do with the bus. The interface does not let it happen. There's no provision to read and write at the same time. SAS. I'm not sure what is SAS. Can Chris elaborate on SAS? Bidirectional doesn't mean it is simultaneously bidirectional. So SATA. Serially attached SCSI. SCSI is the same way, yeah, because a SCSI controller is still interfaced usually using a DMA channel, and as a result, it is still only one direction at a time, even though, at different times it can be, reading or writing. Okay. All right. So, so this is an interesting, discussion of the evolution of technology when it comes to what we perceive as, okay, the content of this device does not change over time. Okay. So now we're going to go back to the simple ROM device over here. And the first thing is, well, if it's read-only, how do we program it, right? How do we change the content? So you might want to pay attention, because this is also something that you need to do for tonight's lab, not for the ROM but for the RAM. But both devices, allow you to right-click on it. So when you right-click, you can see there is a edit content, and when you click on edit content, it opens up an editor which displays the content of the device. So the first thing I need to show you is how do we read this, okay? How many locations are in this particular ROM? So when you click on the ROM component, you will notice that it has width control for the address as well as the data. So the width of the address is controlling, how many bits do we specify the address of a location in the device. So in this case, we're using 8 bits to for the address port, and as a result, we are capable of specifying address 0 all the way up to address 255. And yes, I'm using decimal numbers in this case. But the width of each location is independent to the width of the address, which is kind of saying, what you store in an array, how big of an item you're storing in an array, or the type of the array, is independent to the range of indexes that are valid for a particular array. So A is controlling the address bit, is controlling the index, which is what goes into the square bracket when we access an array. And then the data bit width has to do with the type at each location or of each element in the array. So coincidentally, we are also using 8 here because 8-bit is 1 byte, and that's a fairly common number for smaller devices. Content, click to edit. This is just another way to pop up the hex editor, hexadecimal editor. So once you get into the hexadecimal editor, you will see each row. Okay, there's an address starting each row. So this is the address starting a row. So we start with 00 in hexadecimal, and then the next row starts with 10 in hexadecimal, 20 in hexadecimal, and so on. So within a row, the first item within a row is the actual address as specified by the italic leftmost column, and then the next one is just one after that, and then one after that, and then one after that. So let me just pick one random location here, and I'll tell you what is the actual address of that location. So this particular byte belongs to the row that starts with 90. So that means this byte here, the first byte on that row, has an address of 90 in hexadecimal, and then 91, 92, 93, 94, 95, 96, and this is location 97. Once you highlight a particular location, you can manually change it. Now, this really does not correspond to something that you can actually do in ROM, but since we're using a simulator, it is, we can do certain things that the physical device cannot. Maybe not today, so we'll see how far we can go today, Andrew. So if you want to change the content at just this location, you just type over it. So let's just say that I want this content to be 7E at this point. You just type 7 and E on the keyboard, and that changes the content at that location. Can I pick 7 instead so we could see? Pick 7 what? 7 for what? 7 for the address or 7 for the content? 70 row. Okay, so this is 70. Oh, okay, I see. My picture is covering it. Okay, sorry about that. I did not realize. Okay, so now we can see it. Sorry. So this is location 97 because this is 90, 91, 92, 93, 94, 95, 96, 97. And then once you highlight it, you just type over using the content like 7E in this case. There we go. Okay. All right. So when you're done, you can just close the window. There's no need to save it. Save is useful only if you want to save the content of the ROM into a file. Now the really kind of cool thing, is if you close this window, you either close the window using the X little icon here or clicking close window, the ROM is actually changed. But since this particular window is fairly small, it only displays locations 00 all the way up to 0F in this case. So the location that we have changed is not shown here. Now the location that we have shown is 97. So now we can try to specify the address corresponding to 97 and see whether we can get the content back out here, which is supposed to be 7E. So we have to do some base conversion because this is all binary. The input pin and the output pins are binary, but the content in ROM was specified in hexadecimal, and so is the address in ROM. So now we switch to the poking tool, and I want to address location 97. So 97, we start with a 9. 9 is 1001. So we click this to a 1, and then we click this one to be a 1. That's a 9. And then 7 is 0111. So we can now change these 3 bits into ones. And then you guys go like, but nothing happens to the output. What is going on here? Well, that's because we haven't selected. Okay, the chip is not even paying attention right now. So we have to make sure that the select bit is a 1 in order for the device to actually pay attention and output something in the data port. So once we switch the select pin to a 1, we can see that it is now addressing location 97, and it is not what I was expecting. Okay. No, I don't think we have to reset the simulator. We'll check the content again, and it is 7E over here. Okay, it works for you. All right, so we'll go ahead and reset simulation, and then change the ROM. When you reset simulation, you're not zeroing the content of ROM, so the content of ROM would still be here. And we can double check pretty quickly. We can just go to edit content, and we can see that location still has 7E in it. And now we specify the address again, 1001 for the 9, and then 0111 for the 7, and then turn on the chip, and it is now at 7E. Okay, so there's a little bit of a disconnect somewhere within LogiSim, that it did not update, the content editor does not update the actual device content. Oh, okay. Well, that means it's a little buggy. But now we look at the output. Okay, now we look at the output and say, are we getting 7E back? 0111 is a 7, and then 1110 is an E, so we did get the content back. So this is basically how you make use of a ROM component. Is you're just pre-storing something that is not supposed to change over time, and we specify the address so that we can specify which location we want to retrieve. And once we have the selection pin being a 1, the content at that location will be presented onto the D port, and then you can do whatever you want with the D port, the output of the D port. So do we have any questions about what a ROM is and how to make use of it? All right, I'm not seeing any questions. Oh, here comes one. The TTP has no endianness because it has no multi-byte capability. Everything is 1 byte wide. we only have to worry about endianness, little endian versus big endian, when some parts of the processor has a bigger size than other parts. Then we have to say, okay, when we specify something bigger, do we specify the least significant part first, or do we specify the most significant part first? So that's why the TTP does not have endianness that is built into the processor architecture, simply because everything is 8-bit wide. The address is 8-bit wide, the data is 8-bit wide, the registers 8-bit wide, the ALU 8-bit wide, so everything is only 8-bit wide. So there you go. ROM is not really a place to store data that you can input, because the content of ROM is determined when the product is shipped out, and not supposed to change after that. So if it is something that you can input, it cannot be stored in ROM. And then the last one, yep, okay. All right, so are we ready to move on to RAM? Random access memory. All right, so let's go to test RAM. So you can see test RAM has got a few more components. So we'll explain each one individually, and then we'll do some stuff with it. Sure. All right, so RAM has an A port just like ROM, so it serves exactly the same purpose. It allows something outside of the RAM component to specify an address, so that we can say which location are we talking about. So it's kind of like the page number in a book. Okay, so the A port allows us to specify which page, and then the content of that page is presented or input through the D port in this case. All right. Yeah, you can build your own ROM, but it's really a kind of a hassle. You can build everything using just transistors, but it is a hassle to do it that way. Alright, so it also has a D port, but this time we can see the D port is hooked up a little bit differently. It's quite a bit more complex, because instead of just having an output pin corresponding to the D port, it also has an input pin. This is because we can update the content of RAM on the fly. Okay, so before we talk about this little complex thing over here, we'll talk about the other pins. Just like ROM, it also has a select pin, and once again, the select pin is really just saying should this chip be paying attention or not. So if select is a 0, that means this particular chip is not paying attention at all. So it is not interpreting the address port. It is not going to do anything about the D port either. ROM stores code that never gets changed. That is correct. And I'm just reading the text channel, and I'm going back up. So would a use of ROM be maybe like an instruction set? Yes. So it depends on what you call an instruction set, Anne-Marie. Because in text toy processor, the only purpose of the ROM is to store the microcode. Okay, so it's a little bit different compared to an actual conventional computer, where you would have some ROM to store the bootstrap code for that computer. And then going back up a little bit more, how can I learn how data is stored as addresses? So it depends on whether it's a ROM or RAM. If it is ROM, sometimes it literally is whether a fuse is broken or not. That's how one OTP stores its data. Basically, when you quote unquote store data, you're basically destroying certain fuses, so that the data would be read as a 0 or 1. When you're talking about RAM, you can kind of look at RAM, each bit of RAM, like a D flip-flop. That's one way to look at it. Okay, so you can kind of look at it that way. Yes, very old game cartridges are ROM. They are definitely read only. Yep, cool. And you can download game emulators, okay? And if you can find a legal source of the cartridge, the content of the cartridge, you can play, Atari 2600 games on the PC. I mean, yeah, kind of cool. All right, so now getting back onto the discussion of RAM, the next one is clock, okay? So the clock pin is doing the same thing as the clock pin of a um, edge sensitive D flip-flop, because a RAM can update. So the question is, how do we control the timing of the update? And the clock pin is exactly for that purpose. When the clock pin goes from 0 to 1, that is when the content of RAM is updated. Now that part is configurable, so when you select the RAM chip, you can see data interface allows you, oh, maybe not. Okay, so RAM actually does not allow you to change the edge direction, when it updates. It has to be a rising edge. So the load pin is the funny one. Okay, so this is starting to get a little bit interesting, because the load pin actually controls, are we reading from RAM or are we writing to RAM? When the LD or the load pin is a 1, we are telling the RAM chip and say, we are reading content from the RAM. When the LD pin is a 0, then we are supposed to be writing to the RAM. So I'll illustrate these with examples later on. The clear pin is kind of the reverse, or the polarity is reversed, but the purpose is the same as the reset. So when the clear pin is a 1, then the entire content of this RAM chip is zeroed. Okay, it's erased. So clear should be a 0 most of the time. Okay, only when you want to change every single byte in RAM to 0, then you want clear to be a 1. Okay, so now we have discussed all of the ports of RAM. So now we want to go like, I want to program location 97 with a content of 7E, which is sort of what we did with ROM, but we are going to do it without using the edit content interface that you saw a little bit earlier. So RAM has the same kind of thing, but we're not going to do it this way. Okay, we're going to do it some other way. So what we'll do is we'll first have to specify the address, right? Because if you want to change the location of 97, then you have to specify the location first. So we say, okay, let's go ahead and specify 9, 1001, and then 7, which is 0111. Then go like, okay, but we want to change that content, change the content of that location to 7E. So the next thing we need to do is to specify data in to specify 7E. So now we have 0111 for the 7 and then 1110 for the E. So at this point, because the RAM chip is not selected because the cell pin is a 0, so the RAM chip is not paying attention at all. Okay, it is just doing absolutely nothing. Okay. But before we turn on the select pin, we kind of have to make sure that the L pin is selecting the correct operation, and it is correct, okay? Because we want the LDB, the load pin, to be a 0 to specify a write operation. So now we can turn on the RAM chip and say, hey, we got everything set up, so please pay attention now. Okay, so we turn on the select, and you can see right away it highlights the location of 97. Which basically means, yes, I know we want to do something with location 97, but it's not updated yet, because the timing of the update is controlled by the clock pin. Only when we have a rising edge at the clock pin will the data be going into be programmed into the RAM. So here comes the other two components. Okay, this component here and also this component over here. What are they doing? Because 94 is referring to the first byte of the row, and this is not exactly 94. This is 94, this is 95, 96, and this is 97. That's why. All right, so now we need to explain these two extra components before we actually make the rising edge. So this component, okay, so if you want to know what component, if I give you the circuit, this component is called a controlled buffer. So a control buffer is kind of like a clutch, okay? If you're okay, I suppose most people don't understand what a clutch is anymore, because the number of people who drive a stick shift or manual transmission is becoming smaller and smaller. Even car thieves don't know how to drive stick shift anymore. That's just interesting. I guess I don't have to worry too much that my car is going to be stolen. Exactly, exactly. It is shameful, to be a car thief and not know how to drive a stick shift. Oh, a stick shift is a five, also known as a quote unquote 5-speed or manual shift. That's when you have 3 pedals instead of 2. And sometimes, depending on your technique, you might need to operate all 3 pedals with only 2 feet at the same time. That's what I do, with double clutch downshift. Fun stuff. And for those of you who want to know what is double clutch downshift and why you want to learn how to do that, I would suggest that you watch Initial D, the anime, not the live action. Live action is awful, but the anime is great. Exactly. Learn how to drive watching Initial D. No, 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 no. That's actually a very, very bad idea. I don't want people to be ending up, driving their cars over a cliff and dead, end up dying. Yeah, Deja Vu. I like that song too. I like that music. All right. So it's kind of like a clutch. So what it does is when this pin here, the middle pin, when this pin is a 1, then the input and the output are connected. When this pin is a 0, then the input and the output are not connected, and the output is basically doing absolutely nothing if the middle pin is a 0. That's basically what a controlled buffer does. So you can kind of look at a control buffer as it's kind of like a switch, okay? The wire that I'm clicking on here, this wire is basically a switch. It's basically controlling whether the input should be connected to the output or not. That's basically what it is. This thing over here is just a negation, okay? So it will take whatever LD is, negate it, and then use the negated LD to control the controlled buffer. So when LD is a 0, the buffer is going to connect the input to its output, which allows the data in input pin to present the data to the D port of RAM, which then allows the RAM to update based on the D in pin. So we'll talk about what happens when this Y is a 0. Okay, so we got some questions here. So you don't have your D in and D out signals mixing. They're not, how should I put it? D in is sometimes connected to D out and other times not. Okay, so I'll illustrate why that is the case. Because sometimes we want to read the content from RAM, and we don't want a fight between D in and D itself. So we'll get to that point in just a little bit. Okay, so we'll get to that in just a little bit. So right now we have configured everything, because you can click on this wire. Okay, so if you use the poking tool, you can actually see what the wire has as its content. So this one is 7E. That's pretty easy to understand because it's coming from D in, and we specify the bit pattern for for 7E. And this one is 7E as well, because the controlled buffer is turned on. It's connecting the input to its output. So 7E is now presented to the D port of RAM, and RAM is configured for write operation. It is paying attention, and the location that we're going to overwrite is 97. So everything is now set up except for the rising edge. So when I when I change the clock pin from a 0 to a 1, then it updates the content at that location. Okay, so this is kind of cool, right? So next, we want to change the operation. So this operation is done. This is called a write memory cycle. You go to RAM, and it is now done. So when everything is done, it is always a good idea to turn it off. You'll turn off the RAM and turn off the clock. And now we want to configure for the next operation. So let's just say the next operation we want to read back the content of 88, okay, which is supposed to be 00. So now we go ahead and configure the address port first. Okay, so we want the address port to be 1000 and 1000. So that specifies 88, which is the location that we want to read from. We want to specify a 1 for LD because this time we want to read and not to write. So we need to change LD from a 0 to a 1. And that is all we need to do. Okay. So now when we turn on select, okay, let me just catch up with the text channel before I click on the select pin. Alright, so Alexander said, mine says, that's because I have changed the radix of my base. You can change that too. 126 is the decimal version of the same bit pattern. So if you want to change the radix, because I have used the same Logisim for semesters, so sometimes I have made changes and not realized that mine is no longer stock. So you go to Preferences under Window, and then you get a dialog box, and then within the dialog box, let me see if I can remember where this is done. I suppose you can go to Window, New, Layout. Yep, there we go. So if you go to the Layout tab in Preferences, which is under the Window menu, you go to the radix. Okay, so first radix is binary, and then I have my second radix as hexadecimal. The default, I believe, is signed decimal. Signed decimal is the default, and I have changed mine to hexadecimal. So this is how you can control, when you click on a wire, whether it displays the value on the wire as in hexadecimal or in signed decimal or in unsigned decimal or in binary. So you got some choices over there. There we go. Okay. So now I think everything is good. Okay. So now we can go ahead and ask the chip to pay attention. So this will happen right now. Ding, like that. So this time, we also want to take a look at the controlled buffer as well as the LD pin and see how it's configuring everything. So without this thing here, we would have a problem, because if I click on the content, you have to use the poking tool in order to see the content. The content of this wire is specifying 7E, but the D port wants to specify 0, right? So without this thing here to separate the input pin from the output of the RAM, we would end up with a fight. We would end up with what we call a bus fight. Okay, because it's not an update. If you're not updating, you don't need to control its timing. Alright, so what I want to do is I'm going to hand draw a wire going from here, directly bypassing that thing into here. And we can see that now we have a problem. And the problem is displayed by the wires going in red. And you can also see, the output. If you click on the wire, it will show you the content. Okay, I have to switch to the poking tool again. Pretty sure there's a shortcut to switch to the poking tool. So when you click on the wire, it shows 0 EEE, EEE 0. So the 0 means both are trying to specify the same for that particular bit, so it's okay. But the E is specifying that one wants to specify a 1, the other one wants to specify a 0, so it shows up as a E, because now we have a quote-unquote bus fight. Because they're not agreeing on what the state of that pin should be. So in reality, what happens in a bus fight, right? I mean, because in a simulation, we can basically just say, oh, logic sim, identifies that, we have two outputs. One output wants to specify a 1, the other output wants to specify a 0. So, we have an erroneous condition here. In reality, you have transistors, right? So you have transistors, trying to fight each other. So you have basically one side having the P transistors connecting a conductor to VCC, which is the positive, voltage, and then the other device has the N transistors connecting to the ground. So now you have a very short, a low resistance path from the positive voltage all the way to ground, only going through the transistors. For those of you who have taken physics, in electrical stuff, you will know that if the rails are hard, okay, which means your power supply is very, very good, so they can basically supply an unlimited amount of current, okay, and while maintaining the voltage. So when you have devices in between, okay, this part I think it's better to use a tablet to explain it. So what you end up with here is you have VCC, on one side, and it's going through, one or more P channels. And then on the other side, you have another device that is going through a N-type device and going to ground. And they're on at the same time. So when this happens, this is actually the quote-unquote output, okay, which is erroneous. It is identified by E in simulation. But in reality, what is happening is you have a huge current, okay, going here, over here, and then going to ground like that. The resistance offered by the transistors typically are fairly low, so we are looking at a pretty large current here. And if you remember your physics, for those of you who have taken physics, let's see, I is V divided by R, and then power is IV, which is then V squared R, right? So depending on the resistance of the transistors, okay, so depending on the resistance of the transistor, you would have this much power, dissipated by both of the transistors. So now the question is, what is going to happen, if I have a configuration like this, okay, inside the processor, what is going to happen? Exactly, the transistors one of the transistors will end up dying because it's going to overheat. And some people may ask, what do you mean by overheat? Okay, does it just get hot? No. Does it get molten? A little more than that. It actually gets vaporized. It actually gets vaporized. And if for those of you who are saying, it is not possible for anything to vaporize inside the processor, I would refer you to this YouTube, okay, AMD processor explosion. It's a pretty good one. And let's see here. There we go. So you can watch this yourself, when you have time, but it's actually pretty impressive, okay? Because it is not just exploding; it blew a hole on the table that was supporting the motherboard. So the explosion did not just melt the chip, okay? It did not just explode and make the chip disappear. The explosive force was large enough that it blew a hole on the motherboard. And for those of you who have worked with motherboard, you know the FR4 is not a flimsy material. You don't just punch through FR4, easily. Okay, you can use a screwdriver and jab at a motherboard, and I think most people cannot, poke through a motherboard. Okay, maybe repeatedly you can kind of, do that, but with one stroke, no. But this chip actually blew a hole on the motherboard and then blew a hole on the table itself. Yeah, it's I guess you can call it a shape charge. Now, don't look up shape charge in Google, okay? Because Homeland Security will basically be alerted, and someone may knock on your door. But it basically became a shape charge where the energy is directed only in one direction, so it would appear. Yeah. Yes. So basically, it vaporized the content of the chip. And this is not even from a bus fight. This is just because someone was saying, "Hey, what happens if I just remove the heat sink, while we are running, a torture test on the processor?" And it just blew up. Basically, it literally blew up. Or I should say, blew down because it blew a hole underneath and not up. Yeah, kind of cool. So that's why we have so all of this, okay, so getting back, see, I have to get back to the context of this whole discussion, is we don't want a bus fight, right? So if you don't want a bus fight, you basically have to get rid of this straight connection and then use a controlled buffer so that we basically avoid that situation from happening. Because right now, this wire is disconnected from this wire because the control buffer has an input of 0, which literally disconnects the input from the output of the control buffer. So there you have it. So that's how RAM works, okay? And let me look at the time. We got 20 minutes. This is perfect. How does DIN get into RAM? Well, what do you think? Look at the diagram. So this is DIN, right? The DIN goes into the control buffer. When we want to update RAM, the control buffer will be turned on. And when the control buffer is turned on, then the signal will go to this end, and then it will be presented to the data pin of the RAM. We did that before, okay? We performed a memory read, a memory write cycle before we illustrated this particular read cycle. Oh, okay. All right. All right, so the other question is, as far as I understand, the D port can receive and output data from ROM. Well, if you have a ROM, the D port can only output, cannot input. It's only when you have a RAM then the data port can also input, because RAM can be updated. Alright, next question is, how does the RAM data port act as both input and output? Internal to the RAM component, it also has its own control buffer inside, and that's why it can change its direction. So it's not usual that we have a port on a device that is quote-unquote bidirectional, and the RAM is one of the few components that has a bidirectional port. How did it keep the 7E? Well, the 7E, because it's memory, it's a memory device. Once we wrote 7E into location 97, it stays there until one of two things happen. Until I make clear a 1, or until I reset the simulation. Both will erase the entire content of a RAM component. All right. So it looks like, we got all the basics done now. So now we're going to move on to the actual fun stuff, which is, how do we get the processor to work, and how do we program the processor? So we're going to be doing that now. We have about 20 minutes or so to do that, which is, I think, enough time to do it. Alright, so moving on. So in your homework assignment, you will be given a link to a Google Drive folder. Okay, so that's where you will find most of the good stuff. So let me go to the Google Drive. And it is already shared, at the top of the Canvas shell. So if you go all the way to the top, you will see the shared folder link, and it is going to be in CISP310 you won't see all this stuff here because this is the root of where the content is shared. So within shared, you want to go to processor as a subfolder, and then within processor as a subfolder, the instruction is in the lab already, so I'm not gonna repeat all that stuff. So you don't want to do this alongside with me because the actual instruction to do this is in the lab itself. Okay, so I'm doing this because I already got certain files downloaded. So that's kind of what you need to do in the lab. But once you have all those files downloaded, there's one file that is, or there's one document here that is kind of special. It's called the assembler. So when you double click on the assembler, it is actually a Google Sheet. I turned a Google Sheet into an assembler. And in this assembler, you have a special sheet called source. So when you get to source, the first thing you might want to do is to erase the entire column A, and that's okay. So you just click on column A, press the delete key, and that will erase the entire column. And you can, I do not recommend people typing directly into a cell. You can if you want to, but it's really not the best way to do it. So the best way to do it is to use Notepad or Vim or something like that, And later on in this class, I will show you a syntax highlighted text editor that I find is quite useful, but some of you may go like, no, I don't like Vim. That's okay too. But I'm not going to get there, until later. I'm going to increase the font size just a little bit, because there's no need to use a small font size at this point, because our program is pretty short at this point. So don't ask me what these things are, because that's going to be something that we'll be explaining soon. But you can, this is how we can specify a program. Okay, so LDIA with a 0, LDIB with a 1, specify a no op here, and a halt instruction here. Okay, so this is what you can do with just Notepad in Windows. Any text editor would do. Okay, so you don't have to be specific about which editor you want to use. Control A to select all, Control C to copy, and then go back here. And when you paste, you have to be careful too, because you don't want to paste when you see the blinky cursor here. So when you double click on the cell, you will see the blinky cursor. That is not what you want. You just want to select the cell without the blinky cursor, and then you just Control V to paste the content. And as soon as you paste the content, the assembler will do its work. Now, if I make a mistake, okay, if I say blah, okay, which is not an instruction, the assembler knows about it and goes like, hey, you got a problem with this instruction. So, it does have a certain amount of checking. It's not super smart when it comes to reporting an error, but it will detect errors. Alright, so I'm getting back to the text channel. How do you generate a random string? That is funny. Vim is good. Okay, once you get used to it, it is very, very handy. So anyway, this is my program. Emacs. Emacs is memory pig. That's what it is. So the next thing you need to do, this is also in the instruction, you go to the RAM file tab. Now this part you guys need to pay attention. Is to go to RAM file tab and make sure that you're reading v2.0 raw. Okay, because if you have a syntax error, it won't show v2.0 raw here. And then you go to file, and then you go to download, and then go to one of these two. Okay, either CSV comma separated or TSV, which is tab separated. I personally use CSV for this purpose, so you click on that and save the file. Okay, because if you open it, it would just read like this, so it's not very exciting. So you just save the file into a file. So I'll just say this is test.csv. So now what we have done is we specified a program in the assembler. We look at the output from the assembler, which are the actual opcode. I'll explain, the mechanism of all of these in future classes. But for today, we just want to know how to use the tool chain. So we are not really I'm not explaining how these bytes come to be. And then what we need to do next is to use logisim. So I'm going to go back to this logisim. I'm going to save this file, just in case I want to use it later. So we'll say ram dot, press the enter key, and I'm going to close this, and then I'll reopen it using the processor file. So I'm going to close this, and I'm looking for my terminal program. So I'm going to type the full command here for those of you, who want to know how to do this on the command line because you have Mac OS 10, or later on, okay, trust me, later on, knowing how to use a command line to start logisim, especially to run a text toy processor, is going to be important. Now for tonight's lab, doesn't really matter. Okay, you can use the GUI to start it up, no problem. So we say java-jar, and then we specify the logisim file, which is in my documents subfolder, CISP310 logisim 310.jar. So remember, don't use the one that you download from other websites. You'll use the one that you download from my website. Okay, so that's the one that we should be using. So normally, if I press the enter key now, it's going to start up logisim, but I can also supply the processor file. Now, where you can get the processor file is in the instruction of the lab. Okay, so don't worry about this part, because you will, if you follow the instruction, you will basically know where to get this. Okay. All right. So now I specify the circuit file, and then when I press the enter key, logisim starts up, and this time it starts up with the processor already loaded. Okay, so I'm going to move that out of the way. All right. So when logisim starts, the ROM component is already loaded with this content. So don't touch this. Okay, don't touch this because you don't want to change the ROM component of text toy processor. Okay, it should remain the way it is as you download the file. Okay, so leave it alone. Okay, don't change the content. So what you do want to do is to go all the way to the right hand side of the circuit where you can find the RAM component. And the RAM component always reset to 0 when you first start the processor file. So it's always going to be reset. So what you need to do now is to right click and go to load image, and then go back to the where you saved the file earlier. I believe mine was in the temp folder. Okay, let me see, where is it? There we go. Nope, not that one. I saved it as a CSV file. There we go. So we test.csv, and then open it, and now you can see the content loaded into RAM, and now we can actually run the program. So to run the program, you can single clock through it, which means you can do a Control T over and over and over again, or you can specify a tick frequency and then click on ticks enabled, and then you just let the program clock through the whole program until it's done. So I can just do this, and you can see how the program is actually doing its own thing. So now the question is, but it's still blinking. How do I know it is already done? There's one little indicator here that is really handy. So if you go all the way down here, if you see the halt pin being a 1, that means the program has reached a point where it cannot proceed any further. So that is your clue of going like, okay, I think the program is all done now. So then you can go to simulate and then stop the clock from auto ticking, and then you can inspect things. Okay, so you can go to RAM and inspect its content, or you can go to the register bank and inspect the register bank. So let me show you how to access the register bank. This is the register bank. So don't double click it. Okay, I would just right click and then say view register bank, And when you get here, you can see the content of register A is 0, 0. The content of register B is a 0, 1. The content of register C is a 0, 0. And then the content of register D is also 0, 0. All right, so I'm going back to the text channel to see if there are any questions. Andrew, the eventually will understand the entire circuit. So the schematic of the processor, is to be understood at a later point. Not today. Tonight's lab is about the tool chain and not so much about what is inside the processor. In other words, if the processor was a car, we just want to learn, how to where's the fuel cap, how do we, put fuel back into the car, how do we pop the hood, but we are not really kind of driving much today. We're just going to get in the car, turn on the ignition, listen to the radio, make sure that we can turn on the dome light and turn off the dome light, and then get back out of the car. Yes. The halt pin is behind my face. I suppose I should turn off the camera at some point because my face serves no purpose, right? Oh, okay. I still cannot see it. Let me move me. Oh, okay. I have to right click, unlock preview, and just move myself out of the way. Okay, now you can see the halt pin. It's right here. Alternatively, I can just move myself out entirely. There we go. Okay. So that's generally how you work with this. And let me look at the time. Perfect timing. We only got 5 more minutes. So this is pretty much all you need to know in order to get started with the lab. But from previous classes, I know people will be asking a question. So I'm going to pre-explain that in today's class. So you might see, okay, so this is the assemble tab. And obviously, you only have read access, to this document. You will have to make your own duplicate or your own copy to your own Google Drive in order to do the homework. Okay, but it's okay to see, to share, and have only read access to this one at this point. So what I want to explain is, do you see how these numbers, they kind of skip one sometimes and not skip one other time? And the question is, what is it representing? So column W is representing the address of a particular row, the start address of a particular row. So this row here, row 1, starts with location 0, 0. Row 2 starts with location 0, 2. Row 3 starts with location 0, 4. And then row 4 starts with location 0, 5. So the question is, how come we're skipping certain things sometimes and not skipping other times? In other words, row 1 starts with location 0, 0 because that's what column W is telling us. And how come row 2 is starting at location 0, 2? What happens to location 0, 1? So when you look at the comment on column X, it is opcode, and then when you look at column Y, it is immediate. So what happens is certain instructions takes up 2 bytes. So the LDI instruction specifically takes up 2 bytes. And the first byte is in column X, the second byte is in column Y. Other instructions, such as the no-op instruction, only takes up 1 byte, so it only uses column X. The halt instruction, likewise, is only using 1 byte, and that's why it's only appearing in column X. So that's kind of the deal, because one of the questions require you to find the content of a particular byte, but it is not the start address of a particular row. That's all I can say. Because I get questions about that one all the time, because people are not associating they're not linking the two the XY column having content versus how the address is skipping a byte on a particular row. So I'm just pre-explaining that one. So hopefully tonight I won't get as many questions about that one. Okay, and we still have 2 minutes and 30 seconds before 6:50. So let me get the lab released so that you guys can start on it. So this lab is called familiarizing with the TTP tool chain. So we'll go ahead, and you cannot see it yet because I have not published this lab yet. And this one is kind of like the usual lab. Okay, you have until 9:50 p.m. to get this done. The passcode is Johnny. It's named after John von Neumann. This is kind of like the first introduction into text toy processor, which is a von Neumann architecture. So the passcode is Johnny, all lowercase. And then we're gonna specify the due date, which is March 9th, 9:50 p.m. There we go. And save and publish. There we go. Alright, so I'm getting back to the text channel. Everything seems overwhelming. Can't imagine I could understand the whole thing in the future. Alright, so one way to look at this, okay? So I'm hoping we understand what a register is. Basically, it is just a multi-bit version of a fancy D flip-flop, right? We explained what RAM is tonight, and we explained what ROM is tonight. Last Thursday, we also explained what a multiplexer is and what a demultiplexer is. Those are basically railroad switches. So you can kind of look at RAM as a warehouse, right? Because you can store things in it, and then later on you can retrieve things. So it's kind of like a warehouse. You can look at the ALU as a factory. Okay, so you put raw ingredients on one end, and then you can get the finished product on the other end. From the other end, registers are kind of like a super efficient but very small warehouse. So you can basically store things and retrieve them later. But in Logisim it doesn't show, but in reality it is a whole lot faster compared to memory. So those are the kind of analogy that you can draw, from real life, things, to the constructs in the processor. So now the question is, how do we look at this schematic? Okay, so let me switch back to the schematic so we can actually see it. So now we switch back to the schematic and say, but this really looks awfully complicated. Okay, look at all those wires going everywhere. So think of those wires as railroad rails. Okay, so now you have factories, you have warehouses, right? And then you have switches, and then you have rails. That's it. Okay, so that's one way to look at this. Okay, is you just have a whole bunch of. Okay, so I'm gonna part you with this diagram or this link here. I think it is Thomas the Tank Engine Sodor Island map. There we go. Just look at the processor as a fancy version of this. Okay, where's the picture? There we go. There you go. This is kind of the same as this over here. So just imagine you have a whole bunch of little trains, okay, and they go from one thing to another thing. These are the railroad switches, okay. The multiplexers and the demultiplexers are railroad switching devices, okay. So all they do is go like, okay, the input track is going to connect to this output track, or one of these input track is going to be connected to the output track. The rest halt, okay. You cannot get through. So that's kind of what it is. Just like in Soda Island, there's the fat controller, right? The fat controller equivalence is this mechanism down here. This is the fat controller. Basically he's the guy who's controlling the island with all these switches and whatnot. Okay, um, and the fat controller has a playbook. The playbook of the fat controller is coming from RAM. Those are your instructions. So the fat controller reads the instructions, and then it will flip all the switches to control the switches and whatnot, so that now we can divert, Thomas to go from the output of this warehouse into the storehouse over here, and meanwhile Henry is gonna go from here to here, and then blah blah blah. So it really is. It really is kind of like a digital binary, slightly more complex and slightly more abstract version of Thomas the Tank Engine, Soda Island. And obviously, if I design this carelessly, we can end up with collisions too. We can have, Henry running into Thomas if I don't design this carefully, because, we can have, remember, a bus fight? Now we have a rail fight between steam engines. Yes. But I want to give you this analogy, because I don't want you guys to feel overwhelmed by what it looks like, because all it really is trying to do is to specify, how do we operate, okay? And the analogies that I made, of factories and storehouses and warehouses and stuff like that, it really actually does apply, okay? And we are just really having, we are using electrical signal to bring data from one component to another component instead of having trains to do the same thing. But just like having trains, we also have to use switches to basically say, okay, in order for Thomas to go from this particular factory to this particular warehouse, we need to configure the switches along the way in a particular way. That really is what the processor is doing. It really is just controlling all of those things. So I hope this makes it less intimidating. If you just kind of think about what you're seeing here as a kind of like a slightly more fancy version of this. And for those of you who have not watched Thomas and Friends, I mean, it's a children's show, but I do recommend watching the ones that George Carlin narrated. Those are pretty fun to watch. If you just think about, George Carlin, the comedian, he passed away years ago. But in reality, when he's doing his comedy bits, he swears. Okay, he swears left and right. There's no end to his swearing. But when he did this show, he did not swear a single time. Maybe they had to retake certain scenes a few times. But it was funny. It was actually pretty funny. Yeah, I like him. He's my hero in many ways. Okay. So I think that can conclude tonight's lecture, and you guys can get started with the lab. So I'm gonna disappear for about 10 minutes. I'm gonna AFK for 10 minutes, and then I'll be back to answer questions. And before I go, I'm gonna type tonight's passcode in the text channel, and it is Johnny. And then I'll pin it so that people can find it. All right, there we go. Haha. That is funny. Cool. And thank you, Nathan, for posting the video link again, because, well, I mean, it can come in handy, especially when you guys need to work with the assembler, also, load, code into the RAM components and stuff like that. So that part can come in handy. All right. So I'm going to stop